Welcome to our tutorial. The topic is streamlining the processing of F0 data using the R package intonation. My name is Albin from Kobe University, and this is a tutorial at Speech Prosody 2020. Originally scheduled for May 24th, but actually held online. Before we begin, I recommend you first go to this address and download the code for the tutorial. As you go through the video, I recommend pausing at several points to try running the code on your machine and reproducing the analyses I'm showing. With that said, let's begin with some introductory notes. So what is this tutorial about? What is the scope of content we will be covering? We'll be talking about R package intonation, which is something I released a few years ago. The latest version is version 1.1, released July 12, 2016. I built it on R version 3.3.1, but it does work okay with later versions. And in fact, for this tutorial, I will be using R version 4.0 on Windows. I've confirmed that the package also works on Mac and Linux, so with only small modifications, everything should work okay if you have one of those systems. And this tutorial, in general, assumes you already are familiar with R. If you are interested in the functionality of this package and you don't know R yet, you can check out rproject.org and do some online searching. Next, let's talk about what this package can do. The original purpose that I designed the package for was to assist with the linguistic analysis of fundamental frequency, or F0, in human speech. In other words, I'm assuming that the user wants to process F0 data as part of an acoustic phonetic analysis. And there are other potential applications. For example, F0 data in other domains, animal communication or musicology, etc. But the original purpose was for linguistic analysis of speech F0. Next, I'd like to talk about the relationship between this R package, intonation, and Prot, a very popular software program for acoustic phonetic analysis of speech. If you're not familiar with Prot, you can check this link on the top right. The ultimate goal of the intonation package is actually to serve as a substitute for Prot, so that it can be used instead of it. What I mean is that we want the entire data analysis workflow from the original sound files to the ultimate statistics and plots to be completed entirely within the R environment. Of course, this package does not have functions for statistics, for example, but if you can do your intonation analysis in R, then in theory you can do everything in R. It's kind of the last missing piece. And in order to make this possible, this package draws upon the Prot-R platform, something I developed in 2014. This is specifically needed for just these two functions, but in general, I recommend installing Prot-R before installing the intonation package, and we will see some details soon about that. All right, so let's talk about how to install the intonation package. First, let's talk about package dependencies. As the name suggests, these are two other packages that this package depends on, and both must be installed alongside it in order for the intonation package to function properly. First is the audio package. Fortunately, this is available on CRAN, and so all you have to do is run this line of code. If you are interested in learning more about the audio package, you can check the link here. The second package dependency is Prot-R. For more information about it, you can go to this link. But basically, you just go in there and check under installation. and currently this is what that part of the page looks like. So just follow the steps, and it actually looks like a lot of work, but it's only a few steps. So once this is done, you're ready. So now we can begin installing the intonation package itself. The first thing to do is to download the zip file. So go to this address, and you will see something like this in the middle of the page. On the right side, there's a green button, clone or download, and then it will pop up with this window. Click the blue button, download zip. Once you've downloaded it, you will have this zip file somewhere on your computer. And so what you need to do next in step 2 is to pull out the contents from the zip file. I don't recommend just right-clicking and doing extract. Actually, it's better if you double-click to open the zip file, select the folder inside called intonation master, and then extract that folder somewhere, for example, on your desktop. If you do that, it will look like the top right. Now we have a folder extracted out. And then when you're done with all of these steps, then the contents of that folder should look like this on the right: inst, man, r, etc. There's an important thing to check before you continue. You shouldn't have an intonation master folder inside an intonation master folder. That is a problem that often happens if you just right-click and extract the zip file. If you follow these steps, then that shouldn't happen. The next step is to find the path to that extracted folder you just made. If you unzipped the folder to your desktop, then the path will be something like this. On Mac, users, and then insert your new username in the gray part, desktop intonation master. For Windows, it's almost the same, but there's C: in the beginning. If you need help finding what your username is, for example, on Windows, you can right-click the folder, go to Properties, and then Location is the part where you can copy to find your username. The next step is to simply open R. On Mac and Linux, this should be very simple, but on Windows, there's an extra complication. You need to run R as administrator. To do that, one way is to right-click the desktop icon, and on the bottom you see Run as Administrator. You can also access R from the Start menu, and you will see the choice right there, Run as Administrator. Once R is open, you need to run the installation command. Here is what that would look like in a generic form. Now note that you have to adjust the path for the packages argument, so it points to the path you determined a few steps ago in step 3. So for example, on Windows, if you put your folder on the desktop, then it would look like this, and you just have to stick in your username. If everything works okay, then you should see this with the command you ran at the top, and then these messages generated by R, and the last line is done, intonation. To double check that you have actually installed it correctly, the first thing to do is library intonation. And if you don't get an error, then everything should be okay. Now, note that you have put some things on your desktop or some other place on your computer. At this point, it's okay to delete them. Once you have run the install packages command, things are put inside your R directory deep in the computer, and you don't need these files on the desktop anymore. Now let's get to the most important part of this tutorial, which is a quick tour of the package contents. Before I go into any details, I want to talk about documentation a little bit. Each of the individual functions inside this package has a help file, and you can check these individually. So for example, very soon we will see there is a spectrogram function, and so you can just do $spectrogram to pull up the help file for it. You can also pull up a table of contents for the entire package. Just do $intonation. And this is useful because you can use that as a portal to browse all of the help files for the whole package. Also, there are websites that have mirrored versions of the help files from GitHub. And so if you don't have it installed, but you want to check the help file documentation, for example, to see what kinds of things this package can do, then you can go to this link. In this package, I have included some sample data, and in the rest of this tutorial, we will use that to explore what the package can do. First, there is something called hello world.wave. This is a synthesized voice saying hello world, and the specific synthesizer I used was Flight.
Hello world.
That's what it sounds like. In addition, there's also hello world's pitch and hello world text grid. These are accompanying Prot format pitch object and text grid going along with the wave file. So the wave file and the pitch object and the text grid all form a set, and they're all based on the same utterance. For more details about this sample data, including how it was created, you can check the help file for it. Next, before we actually look at the different functions inside this package, there are a few things you need to do to get set up. Specifically, this involves creating files and folders and variables that you will need for the demonstration. And all of this is based on the sample data. Along with this tutorial video, you have been provided this code. So run these different lines of code. The first line is the only one you actually have to modify. You need to customize the part where it says my username, etc., so that it points to your desktop. After that, it specifies where the package home is, paths to the wave file, text grid, and pitch object. Then it creates a folder on your desktop called wave folder, copies the hello world wave sound to that folder, and then it creates a folder on your desktop called a pitch folder, and then it finds the path to that. All right, now we are ready to begin looking at these functions. As long as you've run all the code on the previous slide, you should be ready to try all of these features. Specifically, we will be talking about 7 different functions built into this package. And I want to emphasize that in the next few minutes, I will be covering each of these very briefly. And if you want to know more details and the advanced features I have built into all of these, you should check the help files. Let's begin with spectrogram. Like it says in the name, this creates a spectrogram of a sound file. So the usage is very simple: spectrogram wave path, and it will create something like this. You can see that this is in full color, but there is a setting to change it to black and white, which is more normal for Prot users. If you want to segment your speech, you can use R's function locator to do that. I don't currently have anything built into the intonation package specifically for segmentation, but it's very easy to do this with locator. So for example, you can use a line of code like this, and then R will tell you that, okay, you clicked at 648 milliseconds. So locator asks you to click on the plot, and then it will return the time value if you have the $X. And finally, you need to use package audio along with this intonation package, and you can use something called load wave inside that package to read in audio data and then plot the waveform. So if you run this line of code for the same synthetic voice hello world, it will show this kind of a plot for you. The next function we'll be talking about is readpitch. Just like it says in the name, this function reads Prot formatted pitch objects into R. So if you go into Prot and you create pitch objects as a part of doing your pitch analysis, you just need to do save as text file. Actually, this function does support other ways of exporting as well. But in general, from Prot, you will save the pitch object as text file, and then you can read that in to R. So schematically, after you've saved it from Prot, it looks like this, and then you bring this into R, into the R environment. If you do this, and then you look at some of the lines of content inside what's inside R, you see that we have time, frequency. If there's no pitch at a time point, then it's NA. Also, Prot pitch objects contain information about intensity, candidate strength, and number of candidates. And so that rich information is contained in this representation as well. The next function we'll talk about is rich visualization, which produces a visualization of your F0 data in such a way that it's easier to see what is signal and what is noise. The usage looks something like this. On the top, you have to specify both the path to your pitch object as well as to the wave file. And in addition, optionally, you can specify labels for the different intervals inside it, as well as divisions in milliseconds. Note that the number of divisions is equal to the number of labels plus 1. To get these millisecond divisions, you can do the analysis in Prot and then bring it into R, or you can just use locator like we talked about a few slides ago. If you run rich visualization, then it will create a plot that looks like this. On the top, we have the waveform. This is derived from the wave path. In the middle, we have the F0 track. And this is where the rich visualization happens because amplitude from the pitch object is mapped onto point size, and candidate strength is mapped onto color. I said that this helps you visually sort out signal and noise. The way that this works is you should look for bigger and redder points as indicators of reliable F0. So if something is green or blue, then it's not very good in terms of candidate strength. And if something is small, then it's low intensity. And both of these things are cues that you probably should not be trusting the F0 measurement there. Finally, on the bottom, we have the spectrogram and segmentation. The spectrogram comes from the wave path, and the segmentation comes from the labels and divisions you specify when you call the function. Next, let's talk about toPitch. This creates a pitch object with a specified F0 range. So for example, you can run something like this. Input is where you have the wave file on your computer. Output is the path you want to save this to. Note that I have chosen a desktop pitch path, so it specifically goes on your desktop, not inside the R package. You also need to specify your F0 range. This is in Hertz. And finally, you can say whether you want to overwrite a file if it already exists. The default is false, which means it will protect you from accidentally deleting data. So schematically, it works like this. You have a WAV file on your computer somewhere, and using toPitch, it lets you do the exact same analysis you can do inside Prot to create a pitch object text file on your computer somewhere. Next, we'll talk about F0 rangefinder. As the name suggests, what this does is cycle through each sound file in some folder on your computer, we'll call WAV folder, and it will help you quickly determine the F0 range for each. And it will save pitch objects with those F0 ranges in a pitch folder. So let me illustrate what this means with an example. So here's the usage. You give it the WAV folder, pitch folder, and there's also a flag to tell R whether you want to allow it to overwrite files if there already are some in that folder. And it will give you a progress bar like this. What number of file are you on? What percent? How many do you have left? It will also tell you the sound file name that you're dealing with. And then it will show you an image like this. The coloration of the pitch contour matches the visual parameters we talked about for rich visualization. So you can see reliable and unreliable F0 points. On the top, it shows the range of F0 that you're currently using in Prot to generate the analysis. So it starts with 74.99 to 500.01. And on the right, you can see within that wide range, what are the actual highest and lowest F0 values. Red 134.2 is the highest observed value. Blue 74.9 is the lowest observed value in that plot. So what you can do is use that information to fine-tune the pitch range. So on the right, I show several iterations of this. And usually when you're processing these files, you try it several times. So if you look at this history, you see that, well, I lowered the floor from 70 to 65 because it looks like in this first plot that some part of the valley is being cut off. Then 65 looked like it was too low, so I raised it up to 69. And then after that, then 500 was way too high. We don't need it to go any higher than 135. And so when you're doing this, every time you see a new plot like this, so it's feedback every time, and when you're finally done and comfortable with your analysis, then you hit a keyboard shortcut. In this case, it's Z. That means go to the next file. In our little demo example, there's only one file, and so it tells you that you're all done, and it shares with you the list of all of the floor and ceiling values you used for all of your files. And you can save this into an R object and save it on your computer. But the overall goal here is that by using F0 rangefinder, in a very short time, it's very quick, you can fine-tune F0 ranges for every single sound file in your dataset, and therefore get more higher quality and reliable F0 data. Next, let's talk about stylize. What this does is it creates a stylization, in other words, a nonlinear schematic quantitative representation of an F0 track. Generally, you use this on interactive mode, which means you have some pitch track visible inside R. Usually it's a rich visualization, and you click on it to mark your turning points. So the usage is very simple, something as simple as this: specify your pitch path, and then R will tell you, please select the contour vertices. A vertex is just a turning point. So where do you see the pitch turning in the F0 track? There's also a non-interactive usage, and I have included this as well inside the code for reproducibility purposes. So if you already have marked the turning points, then you can say, okay, I want to create a stylization for this pitch object with turning points at the 211th pitch point, 489th pitch point, and 1123rd pitch point. And if you do these kinds of things and save it inside an object called stylization, then you can print that and you can see all of the rich information contained in this representation. This information is only useful if you can plot it and visualize it. And so the next function we'll talk about, and the last one in this tutorial, is plot stylization. It's very simple. It draws a stylization on top of an open plot of an F0 track. So for example, here is the same F0 track, and you would run plot stylization. The object you give R is the stylization object, and then it will create something that looks like this. The white circles are the places that the user clicked. I think the reliable F0 started around here, and the first turning point is at the bottom of the valley, and then there's reliable F0 until almost the end. So it's an overall fall-rise contour. And if you're interested in more details of exactly how the line fitting works, etc., you can check Albin 2015. So I'd now like to wrap up and conclude. If you do use this package, I would be happy if you could cite it, and here's how. This is the citation for the R package itself, for the code. And if you want to cite the algorithms themselves, like the explanation behind them, the citation should be chapter 3 of Albin 2015. And you can see the citation for this in the references. Finally, I'd like to talk about future development of this package. What this package can currently do is limited to the functions I developed several years ago for my dissertation. However, it's hoped that this package will slowly grow over time and incorporate many other intonation-related functions. Along these lines, I'd like to invite other prosody researchers to develop these functions further or add new ones to the package. To do so, you can contact me via email or fork the package on GitHub. I'd also like to point out that this package is released under the GNU General Public License version 3 or later. Finally, here are the references. Thank you very much for watching this tutorial, and I hope you enjoy using this R package.